An optimization problem is a kind of problem where we are trying to find the largest or smallest value of something. Right? There are applications of minimum and maximum kinds of problems. And so hopefully you've read through the process, or a way of processing through solving optimization problems. And we'll do just a variety of examples to illustrate the process. So in our first problem, there are two numbers. We don't know what they are, so we'll say one is x, and the other one is y, and they add up to 40. And what we'd like to do is find the maximum value of x times y. So if given two numbers that add up to 40, what would be the maximum of their product? So we'll say the product would be equal to x times y. Now the maximum of this product will occur whenever the derivative equals 0, or if it's undefined. And one issue we have is we've got two variables. But because of our first equation, we can rewrite this. We can write y in terms of x. So y is equal to 40 minus x, which means another way to represent our product is that our product is equal to x times 40 minus x, or our product is equal to 40x minus x squared. Since we're looking for we want to maximize this product, we need to know what's going on at the derivative. Well, the derivative of this, p prime, is equal to 40 minus 2x. And our derivative equals 0 when 40 equals 2x, or when x equals 20. And when x is 20, that means that y would be equal to 20 as well. So the numbers that will maximize the product we found using calculus are when x is 20 and y is 20. Notice we've answered the question because all it wanted to know is what numbers maximize the product. Let's consider another example. In this example, we have a rectangle, and that rectangle has a perimeter of 71 feet. So what we know is that twice whatever the width is plus twice whatever the length is will equal 71. And what we'd like to maximize is the area. So the questions are, what's the length and width to maximize the area, and what is the maximum area? And we know that length times width equals area. Now using our first equation, we can solve this for either width or length. I'm going to solve for width in this case. So the width is equal to 71 over 2 minus the length, which means that our expression for our area in terms of just the length would be length times 71 over 2 minus the length. Or, if we multiply it out, 71 over 2 times the length minus L squared. Now, you don't have to multiply it out. We know we need to take the derivative. You could use the product rule here if you wanted to, and that would be fine. I happen to choose not to. The derivative of our area function would be 71 over 2 minus 2L. And we know that a maximum will occur when this equals 0. So 71 over 2 equals 2 L, and this happens when the length is 71/4. Dividing both sides by 2. And if the length is 71/4, then we can find the width, because the width is equal to 71/2 minus 71/4, and this also will equal 71/4. So the answer to the first question, what are the measurements? Well, they would be 71/4 for the width, and the length would be 71/4. The second question is, what is the actual area? And the maximum area in this case would be 315.063, again always rounding to 3 decimal places, units square. I guess it would be feet square since everything is in feet in the original problem. So we've got a width of 71/4 feet, a length of 71/4 feet, and an area of about 315.063 feet square. Let's consider one more example in this lecture. In this example, we need to find two positive numbers. So our numbers will be x and y, that minimize the sum of twice the first number plus twice the second. So the sum is twice the first number plus twice the second number, and we're told that the product, x times y, is 288, so we want to minimize that sum. Well, if I solve this for y, that means y is 288 over x, which means that my sum in terms of x is 2x plus, what is that? 2 times 288 is 576 over x. And the derivative of our sum expression is 2 minus 576 x to the negative 2 power. We'd like to know when this will equal 0. Well, this will equal 0 when 2 equals 576 over x squared, or when 2x squared equals 576. This is when x squared equals 288. And since the original problem just tells us that the numbers are positive, then I'm only dealing with the positive root of 288, which is 12 root 2. Now I can solve for y. Y is equal to 288 divided by 12 root 2. And this simplifies down to 24 over root 2. Or if we rationalize this, 24 root 2 over 2, which is just 12 root 2. So our numbers are 12 root 2 and 12 root 2. So these are the two numbers that will minimize the sum. In the next lecture on optimization, we'll look at 4 more examples of optimization problems.